What if Earth never had just one moon? What if right now, quietly, there was another object circling near us, not bound to Earth like our familiar moon, but shadowing our orbit in near-perfect sync for decades and planning to stay for another 60 years? In August 2025, astronomers at Hawaii's Pan-STARRS telescope confirmed something astonishing. A 19-meter-wide asteroid named PN7 has been trailing Earth, hidden in plain sight, for over half a century. And here's the twist: it's not a traditional moon. It doesn't orbit Earth at all. Instead, it shares our journey around the Sun with such precision that it weaves in and out of our orbital path like a cosmic dance partner. This isn't just another space rock. It's what scientists call a quasi-moon, part of a mysterious group known as Arjuna asteroids bodies, whose paths mimic Earth's so closely they can remain in our celestial neighborhood for decades. But why has no one told you this before? And more importantly, what happens when multiple near-Earth objects share a track? This tight, could this shadow moon trigger unexpected consequences in future asteroid flybys? Could it affect the trajectory of dangerous interstellar objects like Apophis or 2024 YR4? Or is it simply a harmless stowaway in our orbit? The more we examine PN7's past, the more unsettling its silence becomes. If it's been following us for 60 years undetected, what else is hiding out there? And how many near-Earth objects are already in this kind of gravitational limbo, drifting quietly between stability and chaos? The discovery has thrown a curveball into how we define a moon, how we monitor near-Earth space, and how we prepare for Mars flyby missions and asteroid defense programs. Because PN7's orbit is incredibly Earth-like, just 1.2 astronomical units from the Sun, with a mild 2-degree inclination, it behaves less like a rock and more like a phantom twin. Imagine two runners on separate lanes of a racetrack, never touching, never overlapping, but always in view of each other, looping endlessly in gravitational symmetry. That's the orbital dance we're now watching between Earth and PN7. Except this isn't choreography, it's celestial mechanics. And it raises a far more disturbing question. Are we really the only dominant object in our orbital lane? Or are we just beginning to see what's been hiding beside us all along? The technical profile of 25 PN7 is deceptively unremarkable. Just 19 meters wide, roughly the size of a modest 2-story house. But its orbit is what makes it a scientific anomaly. With an eccentricity of 0.108 and a semi-major axis nearly identical to Earth's PN7 loops through space in such close harmony with our planet that it occupies a gravitational sweet spot. This delicate balance places it in a rare category, not a satellite of Earth, but a quasi-satellite, a body that appears to orbit Earth, but is actually orbiting the Sun, just like we are. These objects don't revolve around Earth in the way our moon does, but from our perspective, they seem to drift back and forth in the sky over long periods, creating the illusion of companionship. This illusion is a product of resonance, two bodies syncing their revolutions around the Sun in a way that one seems to shadow the other. PN7 has mastered that illusion for decades, and the fact that it went unnoticed for so long is even more baffling. Archival images suggest it's been near us for 60 years or more. How does a celestial object mimic Earth's orbital pattern so perfectly and remain virtually invisible until now? One answer lies in its extreme faintness. Being so small and dim, PN7 slipped under the radar of telescopes focused on larger, faster, or more threatening near-Earth objects. But now that it's been spotted, its presence forces a re-evaluation of our sky surveillance capabilities. If PN7 can hide for decades in Earth's shadow, what else is flying just outside our view? Even more intriguing is the question of where PN7 came from. One theory suggests it may be a fragment of lunar ejecta, a piece of the moon blasted into space by a massive impact thousands or millions of years ago. Simulations show that such debris can settle into stable co-orbital positions, slowly becoming embedded in Earth's path. Another theory posits that it originated from the main asteroid belt and gradually spiraled into Earth's orbital rhythm through interactions with Jupiter's gravity. Either way, its current trajectory places it firmly within the Arjuna asteroid class, a loosely defined group of objects with Earth-like orbits and extremely low relative velocities. And this low velocity is what makes PN7's presence so unique. It's not racing past us like a typical asteroid. It's loitering, sticking around, remaining entangled in Earth's gravitational influence without ever falling completely under our control. This near-constant proximity has led scientists to start asking, could PN7's orbit interfere with future space missions or other incoming asteroids? Especially when objects like Apophis, scheduled for a record-shattering Mars flyby and Earth approach in 2029, are already creating headaches for orbital planners. In theory, a quasi-moon like PN7 might gravitationally nudge another asteroid ever so slightly, shifting its trajectory in a way that doesn't become visible for years. And when those trajectories involve planetary flybys or even impact probability calculations, even a slight deviation could have cascading consequences. As we look ahead to the coming decade, the timing of PN7's arrival becomes deeply significant. Not only is this quasi-moon quietly looping Earth in the background, but it will be doing so during a period marked by two of the most anticipated asteroid flybys in recent memory: Apophis in 2029 and 2024, or just a few years later in 2032. These are not abstract space events. Apophis is projected to pass within just 32,000 kilometers of Earth's surface, closer than many of our communication satellites. And 2024 YR4, though smaller at around 67 meters across, has been given a non-negligible chance of crashing into the moon. On their own, these objects already demand precise calculation and long-term tracking. But with PN7 now acting as a resident drifter in Earth's orbital zone, the calculus changes. Though tiny in mass, PN7 is not entirely irrelevant. In a region of space where even millimeter-scale adjustments can radically alter an asteroid's trajectory. Over time, the very presence of another gravitational body, even a modest one, introduces uncertainty. One theoretical risk is a three-body gravitational interaction. PN Apophis, or 2024 YR4 in Earth. Even if each object remains in its own projected lane, the complex tug-of-war between their individual gravitational fields combined with the Sun's overarching pull could introduce subtle course deviations over months or years. While astronomers currently calculate that the odds of PN7 physically affecting these flybys are extremely low, the unsettling truth is that low probability does not mean zero risk. The same principle applies in orbital mechanics as in weather prediction. Tiny unmeasured variables can amplify into massive divergences, given enough time and sensitivity. And here lies the hidden tension. The space around Earth is not empty. It's increasingly populated not just by natural objects like PN7, but by human-made satellites, defunct spacecraft, and space debris. Introducing yet another orbiting body into this crowded theater raises ethical and scientific questions. Are we truly in control of our orbital neighborhood? Are we still underestimating its volatility? Some scientists propose that quasi-moons like PN7 could even serve as test beds for long-term gravitational studies, an opportunity to observe how micro-objects behave in Earth's vicinity without direct intervention. Others are less optimistic, arguing that such objects left unmonitored pose navigational challenges not only for future asteroid mitigation plans, but also for deep space probes and even upcoming Mars flyby missions. Imagine a future scenario where a Mars-bound spacecraft executing a gravity assist maneuver around Earth has to account for a faint 19-meter rock that barely registers on early detection systems. It may not pose a direct threat, but a miscalculation in PN7's drift could lead to rerouting, loss of velocity, or in extreme cases, mission failure. And yet the public remains largely unaware of this new guest in our skies. Unlike the moon, which inspires poetry, or comets that ignite public wonder, and exists in scientific shadow, important enough to track, but not glamorous enough to headline. It orbits in metaphorical darkness, a reminder of how little we still know about the space around us, and how many interstellar objects like 3I Atlas or green flash anomalies may still evade our notice. The truth is, PN7 may be just one of many, a minor figure in a growing chorus of space bodies quietly co-orbiting with Earth. If even one of them were to nudge another object by impact, by gravitational deflection, or by disrupting solar radiation pressure models, the consequences could ripple through years of mission planning and planetary defense simulations. In that context, PN7 stops being a curiosity and becomes a variable, a wild card, an unknown known hiding within Earth's blind spot. So as the clock ticks toward 2029, the question isn't just what is Apophis going to do, but rather how many other silent players are already influencing its path. For now, 2025 PN7 remains a ghostly sentinel, drifting with us through space, quiet, consistent, and, at least by all current models, non-threatening. Its path has been analyzed, its orbit simulated, and the verdict seems clear: no immediate danger. But in orbital mechanics, the key word is never danger. It's change. Even if PN7 never collides with Earth or nudges another asteroid, its long-term presence in our orbital zone forces us to confront a deeper issue: how we track and interpret the near-Earth environment. We like to believe that space is vast, that threats will come with warning, that nothing hides in our planetary backyard for decades without being noticed. But PN7 challenges that assumption. It slipped into Earth's orbital rhythm, lingered for 60 years, and we only noticed in 2025. What if it had been more meters on Mainam? Would it still have gone undetected? Would we still call it harmless? The truth is, size doesn't determine significance. Invisibility does. And PN has been invisible. Now that it's on the map, astronomers will keep tracking its drift until it likely exits the quasi-moon state around 2083, shifting either into a horseshoe orbit or drifting further into solar territory. But that's not the end of the story. The discovery of PN7 is not an isolated event. It's a reminder of a hidden class of solar system travelers. Arjuna asteroids, quasi-satellites, co-orbitals. They don't grab headlines like interstellar visitors or Mars flyby missions, but they matter. They reveal how dynamic and crowded our solar lane actually is. They raise flags not just for scientific curiosity, but for mission safety, satellite navigation, and planetary defense. The presence of a near-Earth object in quasi-satellite orbit for 6 more decades may not sound dramatic, but in space strategy it's a wild card, especially as the world prepares for new waves of activity. Asteroid redirection tests, NASA's DART follow-ups, Mars sample returns, and even civilian deep space ventures. In this new age of space exploration, PN7 is a variable that we didn't account for and likely won't be the last. It might not be the object that changes history, but its discovery changes context. It reframes how we define proximity safety and control in the solar system. More importantly, it asks a question far bigger than itself. If we only just found PN7 after 60 years, what else is hiding along Earth's path? What other unseen travelers share our journey through the void, quietly shaping the future in ways we haven't yet imagined?